Thank you for sticking around for the final keynote. I know we're all waiting for the ice cream social, and you guys are probably killing time. So I'm going to try and keep you engaged for the next 45 minutes so that we could all go and enjoy our Sundays. So I'm going to talk about RethinkDB. And when we were thinking about what to talk about in this keynote, we wanted to talk about more than RethinkDB. We wanted to talk about the general phenomena that we believe is happening. And it's this idea that the next couple of years are going to be great for just database technology and for innovation in database technology. We really feel that there will be a lot of companies springing up that do very interesting things in databases. And we're going to talk a little bit about that and, of course, present some of the technology that we've been working on at RethinkDB. So the question everybody is asking us is, why start a company? Like, why start a new database company? Why start a company now? And what are you guys doing that's so different? And I'd like to answer this question for ourselves, of course, what we're doing differently, and why I think this question is pertinent for a lot of other people, a lot of companies that we believe are going to start up. And to do that, I'm going to tell you a little bit about how RethinkDB got started and how we started developing this technology and how we started this company. So I think in about 2008, I joined a PhD program at Stony Brook University over on the East Coast. And what happened was I was kind of looking around, walking in the computer science department, talking to different groups to see what I want to do for the next couple of years. And I found something that I thought was very peculiar. When I was talking to the file systems people, I just said, hey, guys, what are you doing? What are the interesting technologies? What's the research you're working on? It turned out that the file systems guys are working on really, really interesting stuff, like stuff people care about. They're working on distributed file systems. They're working on asset compliance and sort of atomic operations in file systems, just things people really care about outside of the academia. Now, when I walked to the database department and I said, hey, guys, what are you working on? They were working on stuff like, semantic web and logic databases. And basically, if you go out of the university and you ask people, well, do you care about this? Like, nobody's going to have any idea what you're talking about. I don't think anybody really understands semantic web. And what I thought was very interesting is, even if you go out of the database group in the computer science department, people still don't know what they're working on. It's just some kind of magic technology that people don't really care about in the real world. So I thought, well, that's interesting, because that kind of flies in the face of everything I learned in the industry when I was working and building financial systems. Because we had a lot of database problems, and these were like pretty serious problems that needed a lot of work. So I thought, OK, well, this seems interesting, because the database research somehow isn't like hot, and people kind of gave up. So I'm going to work on that. And this is kind of how the idea got started. So the first thing me and Mike looked at is we looked at, well, how can we begin thinking and rethinking databases? And the general idea was that, for the past 30 years, since like 1980, people designed these database systems. And the overall architecture remained the same. People haven't changed it very much. And we thought there has been a massive, massive shift in hardware that people kind of adjusted to incrementally. But they never really sat back and said, OK, what can we do? And everybody knows about Moore's law. I mean, you guys all know how fundamental the changes in hardware have been. But I'm just going to put up the numbers just so you could look at it, because the numbers are so staggering. It's just fascinating. So disk space is 6 orders of magnitude cheaper than it used to be 30 years ago. Right? That's 1 million times cheaper. I mean, that's absolutely fascinating. So RAM is about 5 orders of magnitude cheaper. And hexa-core CPUs are now a commodity product. Like, high-end gamers are buying these machines with a ton of cores. And the idea that the same architecture that applied to the old hardware that was there 30 years ago kind of applies to the new hardware now, that just seemed kind of ridiculous. Like, it seemed like a good idea to look into this, because there might be something interesting to design, something interesting about the database architecture to change. So the change about hardware I was talking about just now, that's a very gradual change. It happened over the course of 30 years. But over the past 2 years, there has been this absolutely disruptive change, and the change is solid-state drives. And when I talked to the group, the file systems group in my university, I asked them, what is the most disruptive thing you guys are working on? And they said, flash memory. That's fundamentally going to change everything. And we thought, well, that's probably a good thing to look at, because it seems to affect databases very, very much. And if you think about it, like you could buy flash that's 200 times faster than rotational disks for only 3 times the price, right? And I mean, it's not exactly apples-to-apples comparison, because flash behaves very differently, but it's still a very interesting thing, and a lot of people care about it. So it's absolutely sudden, like dramatic change. And if you think about a different change in computer science or in software that has happened that was so drastic in the past 30 years, like the only thing I remember is probably graphics cards. And graphics cards changed the gaming industry. So I feel like we felt like this kind of thing is as important as the graphics cards used to be for games, except this is important for everything. I mean, this is literally going to change everything. So we thought, OK, we're going to redesign databases. This is where we should start. Now, the question we asked ourselves is, OK, if we're going to design this new architecture, this new system, well, first of all, how much performance can we get out of it? Like, if you put a traditional database on a solid-state drive, you already get a huge performance boost. So the question is, you're going to redesign the architecture, and then you're going to put it on the solid-state drive. Like, what do you get out of it, right? How much do you get? Is it 5%? Is it 20%? Is it 500%? Like, it's not clear. And the worst part about it was, we couldn't know that until we actually started out in building the technology. So it was pretty scary to jump into it. And another thing we were thinking about is, well, what kind of an improvement do you need for customers to care? Because, do they care about a 5% improvement, 20%? So can you improve the databases? Can you make them run faster than people care about so they're willing to switch? And we were thinking about this for a while. And that's actually a question people ask us a lot. And if you think about it, there's these big companies like IBM that have massive budgets, an army of people, very smart people. So the question is, like, how much can we do, and what is the advantage we have over a big company? So we thought about this, and we found out, so after thinking about it for a while and talking to a lot of people, we found out that the answer lies in the fundamental nature of performance for systems kind of software, for infrastructure software. And I'll get back to these questions in a minute, but I'd like to talk about this performance issue first. So, like conventional wisdom, like the things you hear about performance, people usually say, well, premature optimization is the root of all evil. You don't want to do that because programmers are really, really bad at figuring out where the bottlenecks are. And that's absolutely true. But that's kind of a half-truth, because there is more to the story. And the thing about performance, it's really a combinatoric kind of problem. You can't just optimize a single piece of your software at a time and remove bottlenecks. Because if you do that, you're going to get stuck in a local minimum. And I'm going to explain exactly what I mean. So think of 2 examples, right? Recently, there have been quite a few blog posts by the Facebook team, and we posted about this as well, about figuring out an optimal page size for a database. And if you look at that, there are a lot of trade-offs, a lot of things you have to figure out. It depends on your drive that you're using. It depends on the size of the index. It depends on a ton of different things. But ultimately, like, you could figure it out. You do the math, and you come up with some reasonable page size for you that's going to be pretty optimal. Now, there's a completely different aspect of a database, and that's page reclamation algorithms. And when you kind of load the pages into RAM and then you run out of space, you have to flush some out to disk. And these algorithms, there is a tremendous body of knowledge about it. I mean, people research them for many years. And you could, depending on your trade-offs and depending on your workload, you could come up with a reasonable algorithm for this. But now the question is, if you change the page size, right, does that affect the performance of the page reclamation algorithm? And if you think about it for a while, you kind of realize that the answer is completely unobvious, and it probably does affect it. And it affects changing the page size affects a lot of other things, and changing the reclamation algorithm affects a lot of other things. So it's kind of a combinatorial problem where you can't, like, if you start optimizing one piece of your software at a time, you're going to get these performance improvements, but then eventually you're going to get stuck. But ultimately, you could, if you look at the global picture, like all the different possibilities, And you could get much, much, much bigger performance improvements. The problem is they're very hard to get to because, if you think about it, let's say a storage engine has about 10 fundamental pieces or 20 fundamental algorithms that make it tick. And then each one could be implemented maybe in 20 different ways. And if you do the math, it's like 20 to the power of 20 or like 20 factorial or something like that. So it's a really, really big space. And finding solutions here is really hard. So it's kind of a maze. Like, you could do the small optimizations, but you're never really going to find the part of the maze where the real performance benefits lie. And the way to do that, function optimization people figured it out a long time ago that you don't want to always go up the hill. Like, you don't want to always have better and better performance because you're going to get stuck. So what they do is, they go up the hill, but occasionally they take a random walk where they jump somewhere else. So in this case, you'd have a slightly worse, you'd accept an algorithm with slightly worse performance, probably randomly, hoping that you're going to increase overall performance of the system. And if you think about this, this is like a typical big O, algorithms problem where you're considering the growth of the functions, and it turns out that the growth of this problem, the space of possibilities for all these algorithms, it grows much, much faster than any money you could possibly throw at this problem. So if you think of a company like IBM, they have like a $100 million budget, and we have a $1 million budget. Well, yeah, that's a big difference, and the extra $99 million would really help. But ultimately, just the program, this whole space of possibilities is so huge that this difference in funding, in the grand scheme of things, it doesn't necessarily affect. It won't necessarily give you a big, big edge, or as big edge as it seems, in finding this optimal database performance. So the space for search is huge. I mean, it's just phenomenal. You could change so many things, and you could tweak so many things about a database system that we really believe that a lot of companies will start up and they'll start doing this. And the catalyst for this whole thing is solid-state drives, because now people put databases on them and they expect bigger performance and they care a lot. So the way to approach this global optimum, or the way we think about it, is, well, you could build a modular database system where you could easily plug and unplug different types of algorithms. And then you can run benchmarks and you can see what happens. And you just play around, maybe randomly, maybe semi-randomly. You try different things. And you try to find out like what's going on and how to improve performance. So the way people normally do this is they pick a path. For each algorithm, they pick some solution, and they go up the chain until they build a complete system. And then they start playing with them and switching them and sort of playing with performance. So this is what we did. And of course, the initial chain of ideas, it wasn't very random, because we were designing for solid state. So we picked different algorithms for the storage engine that we thought will work well on solid state. It was just basically an educated guess. And I'd like to talk to you about some of these ideas and this initial chain of optimizations that we took. And I'll get into later how this changed over time. So Jim Gray, the notorious database researcher, had this quote in one of his papers. He said, "Update in place is a poison apple." It's this idea that you never really want to modify a piece of data in your database in the same location on disk. You want to write it somewhere else. And he brings this beautiful example from, I think, accounting, where historians found they found clay tablets of accountants that literally copied everything over, and they kept doing it. And accountants today, even though we have computers and we have paper, they still do it because it's a good way to manage your data. And database researchers and database people that implemented them, they could never really do that. And the reason is because basically of performance. If you started to write in a different place on a rotational disk, you kill performance, and ultimately your system is useless. Now with solid-state disks, all of that changes. So actually, writing in a different location is good for solid state because of the complicated physics that goes on under the hood. And the idea is, if you've heard of log-structured file systems, it's basically very similar. If you have a table, and this is a very simple example of cities with primary keys, if something changes in the database, you only append to the end. So like if you delete the row, you append a record at the end of the file that the row is deleted. Or if you change something, you always append records. So the way to think about this, and I'll get into indexing in a little bit because it's very complicated, but the way we think about it, if you go up from the bottom of the file and you look for your primary key, eventually you're going to find it. And the first record that you see, well, that's the record that you want. And this restructuring, the fact that you're not changing things in place, gives very, very fundamental properties to your database system. So the first one is that you always have a consistent view of the database. So if you think of this dashed line, like everything that happens below it, all the changes, they don't affect anything above it. So if you want to run a long query, for example, it's very, very simple because it's not going. You don't have to lock anything. You don't have to interact with existing transactions. It's very simple. You just read back from the file, whatever was there, and you never have to interrupt anything. And one of the major problems with database systems today is if you have long-running queries, in addition to short-running queries in the same system, that's very problematic. So just long-running and short-running queries can coexist peacefully. Now, another thing you get out of this structure, the log structure, is the fact that you essentially get instantaneous recovery from power failure. And the reason why you get that is, well, you always write to the end of the file. So if your system fails, all you have to do when you start up is you go back through the file and you find the last valid location where you wrote things, and you just get rid of everything else and you're done. You don't have to read a separate rollback log, and you don't have to reconstruct the system in a consistent state. I mean, it's all just there. There's nothing special you have to do, essentially. So another application of this is, of course, hot backup. And the reason is that it's the same thing as effectively as instantaneous recovery. I mean, if you want to do hot backup, you just copy the file live. And the interesting thing about it is, it doesn't interact with any other transactions. You don't need to run any special tools. You just copy the file over, and on the other machine, when you try to restore your backup, you always have a consistent view of the database. You effectively, you look back through the log, you find the last location, and that's it. You get rid of the rest of your data. So it's very, very simple and very elegant. And there are a lot of different elegant designs and elegant things you could do that come out of this, that weren't possible before. So interestingly, every single database right now, or hopefully most databases, MySQL definitely does this, it has all these features. So you could do hot backup in MySQL, right? MySQL or InnoDB does have instantaneous recovery from power failure. It has all these features. But what we found is these algorithms are very, very elegant. And they're just elegant in a way that you couldn't implement this in the same way in a modern system. And we thought that's very interesting because first of all, usually, elegant algorithms have a huge, huge effect on database performance. So we were wondering how this performance is going to be affected. Now, the way I talked about it right now, it's kind of simplified because you can't just read through the back of the file, right? You have to build an index system. And if your index isn't append only, well, then it's, it's a waste of time because even though your other system is append only, your index isn't, and you're not really helping yourself. So you really need to figure out how to do append only indexing. And we looked around and we sort of found out that programming language people did it, in particular like Haskell guys that have immutable data structures. They figured out how to do append only trees a long time ago. And file systems people did it. So for example, ZFS or other file systems that let you do instantaneous cloning of the file system, they figured out how to do this append-only B tree. So, that's one thing we had to figure out. And the algorithm, sort of, if you stare at it long enough, you'll understand that it's pretty hard from the slides if you weren't familiar with it. But I'll try to explain it briefly. And the idea is, you have your append-only index. So you have your B tree, and let's say you're modifying a part of it. Like if you're trying to modify, the third node over there. What you do normally is you go to that place in the B tree, and you try to modify it in place. And if you want to do it in an append-only way, what you do is you copy the leaf all the way to the root of the tree, and you sort of point back the areas that aren't affected into the original tree. So effectively, I mean, that's how it works on a kind of 100,000 foot view. And if you look at it long enough, it becomes kind of obvious. So you know, we thought at the time append-only indexing is kind of solved. It's pretty easy. The only difference is that instead of writing one node now, you have to write like log n nodes, which means that as your tree grows, each write will sort of become bigger and bigger. So if you have a tree of depth 4 or 5, well, now you have to write 4 nodes for every node. So what you trade off is that you always write to the end of the file, and you can kind of batch them together. You can compress them very elegantly. You get all kinds of interesting things. So that's append-only indexing. And once you look at this, you realize, well, it's not just about performance. You could get features out of this that you couldn't have gotten before. And for example, file systems people have very quick, very simple snapshots. You could take a snapshot of a file system, and you could always go back very easily. And it's basically instantaneous. And the reason why you could do that is because you never modify your original index tree. You always have the old tree. Like, it's always there unless you garbage collect it. So what you could do is you could do a kind of time travel where you take instantaneous snapshots. And you could run queries on the database that say, here is a query, what did this data look like as of October 4th, 2009 in our example? Or what did it look like a second ago or 5 seconds ago or 10 years ago? So we thought it's a very, very interesting feature. And it's a very interesting example of how a different architecture can let you do things that you really couldn't have done before. Now, if you think about this, you realize, well, another thing that a traditional database has is it has a separate log where every operation that you do, you write it in the log first. In case something happens, you can always roll back, which has been done that way for a very, very long time. But now if you do it in a log-structured way, suddenly this problem disappears. You don't have to have a separate log, and you don't have to write in a separate place because your database and your index is the log. And it basically cuts the number of writes in half, right? So there is this trade-off. Now we're writing more blocks, but we don't have to write them in a different place because we don't have to write a log. And what we thought is interesting about this is when you start building this initial chain, I'm going to go back to this example of this huge space, combinatorial space of problems. When you go back and you think about this initial space, you start coming up with all kinds of ideas, and we read all kinds of papers. And it's a very, very exciting sort of creative process because a lot of these ideas come together and everything seems to click. Like all of this seems very, very elegant. Right? When you look at it, well, these are really elegant algorithms. If you could implement this, it's going to be great. And then, of course, you try to build a prototype. And it turns out that when very elegant ideas kind of mesh with the real world, well, they're not so elegant anymore because the real world is complicated and messy. And a lot of these things become a lot more complicated than you kind of expected or gave them credit for. So this is actually where the value proposition really lies. I mean, a lot of these ideas aren't new. People have done them in file systems, like Mendel Rosenblum did his PhD thesis in log-structured file system, I think, like 20 years ago at this point. Right? So the ideas in general isn't new. The application to databases, that's new, but it's really not that fundamental. The real value proposition is when you start playing with these things, they become a lot more complicated. And it's pretty difficult to build, to sort of solve these problems in a constructive way where you actually build a real production system that works and is very, very fast, and it gives people significant performance improvements to the point where they start caring and they say, OK, I'm going to switch over. So we don't have very much time, and I don't want to bore you with the technical details of this because they become kind of a lot more complicated than just showing elegant things. But I'll talk about 2 of them specifically. And these are 2 kind of complications that we encountered with our original chain of ideas. And as we built it up, we saw these complications, and we started kind of trying different algorithms, trying different things, and trying to see what happens in hopes of finding this big optimization, the big thing that we're looking for. And the big thing where certain other startups and other companies, big companies, are going to start looking for in the next couple of months or over the period of the next couple of years. So the first challenge is, of course, getting this functional B tree to perform very, very well. Because if it's small, well, it's not too bad. Every time you modify a node, you kind of double the size of the writes. But because you got rid of the log, it kind of balances out. So that's good. But as your B tree grows, and as you're growing, your data set and your indexing grows, this becomes a bigger and bigger problem. And what we found out is, once you get over like a gigabyte of space in the database, that you basically kill the whole system because your write throughput, you just write so much data, you overwhelm even the most modern hardware. So you have to fix this, and the question is how. And there has been a lot of work on this, like the file systems guys thought about it, and the operating systems guys and the programming language people. They all kind of thought about this problem because a lot of them care about functional data structures like this because they're very good for concurrency, they're very good for multi-core, and they have all these very interesting properties. And I'll tell you a little bit about the solution that we picked. And the reason why I won't go into detail because it's much more complicated to describe. Well, I'll just kind of gloss over it. So the basic idea is that you kind of use another B tree on top of this B tree, right? And instead of writing each node all the way up to the root from the leaf, instead of writing log n of the B tree, what you do is you create this kind of virtual mapping system, sort of like what operating systems people created. And the way it works is you give each block its own ID, and you kind of have a second B tree that maps these IDs to actual physical locations. So now what happens is when you modify your B tree, instead of writing the whole thing, you really just write that one node at the end of the file. And then you write the second B tree that does the remapping, that you always look up later on when you need to look up the B tree. Now, the interesting thing about this is the second B tree, because you don't store a lot of data, you only store offsets and like pointers and stuff, it's much, much smaller. It's fundamentally, no matter how big your data set gets, like it's always going to fit into a block. So you always you essentially cut down, or less than a block, actually. So you cut down your write throughput very, very significantly. And it kind of solves this problem, except when you implement it and you try running it, you realize that the second mapping tree has to be really, really, really fast. And if it's not very fast, if it's not cached in RAM, and if it's not just a super fast data structure, you run into all kinds of problems because every time you access your B tree, you have to access this tree, and it has to be really just phenomenal. It has to have phenomenal performance. So the next thing you do, you of course try to optimize your second mapping tree. And it gets, as you start doing this, as these elegant algorithms meet the real world, it gets pretty complicated. And it takes a lot of tinkering and kind of experimentation and randomness and guesses and educated guesses to get it right. But once you get it right, you just fundamentally change the architecture in a way that can give huge performance boost and can actually let people do things they couldn't have done before. So I'll give another example of a complication that we kind of encountered after we designed the original ideas. And we had to change our algorithms around a little bit to account for it. So everybody talks about locking. Like locking is a big deal. If you look at the changes that have been happening in MySQL or InnoDB, the things that the Facebook guys are pushing, a lot of it has to do with locking and the fact that if you run MySQL on modern CPUs, you kind of run into this problem of the lock problem, the fact that you lock the data structures. And what you want to do is generally kind of bubble down these locks to make them more granular, so multiple cores don't run into each other. So what we thought is, okay, well, we're going to have these lock-free data structures. We're going to have lock-free concurrency, and everything's going to be great because we have very few locks or almost no locks, and you really don't run into any problems anymore because each core can run by itself and kind of scale almost linearly. So we implemented this, and we tested this, and it didn't scale linearly, and we had to figure out why. And what we found out is this little feature of modern cores and modern CPUs that we missed. And this feature is called cache coherency, the fact that if you modify something in one cache and you try to read from another cache on a different core, and it's on the same cache line, you kind of run into trouble. And this has been a huge, huge issue for a lot of the lock-free data structures. And the way to sort of solve this problem, it's completely non-trivial. Like there is no, easy sort of plug-in solution, no elegant algorithm that you could use. You really need to think very, very carefully about how you access data, about what you do with it, how it's accessed from different cores, where it lies in the cache, all kinds of things, all kinds of complications. So again, we tinkered with this for a bit. We kind of read a lot of papers, and we figured out how to solve this problem. And eventually, once you put relevant things on different cache lines, and once you sort of the things that you can't put on different cache lines, you redesign your algorithms, not only not to lock, but also not to write things where they don't have to be written, so you don't run into this cache coherency problem. Well, things run much faster. And you kind of go back to this original idea that, well, you can improve performance very, very much by playing with these things. So these are just two things we've been working on. Now, again, there is like about 15 or 20 fundamental algorithms in the storage engine that make it run. And with each one of these algorithms, because you try many of them, you kind of encounter many of these different problems. And it has to be worked out every time. It has to be played around with and tinkered with. And it's very, very difficult work. It involves a lot of benchmarking and a lot of testing. But ultimately, you kind of build a system, and you realize you have something really great because you tried things that people haven't tried before just because it involves taking a risk. And for a startup, it's so risky anyway, it doesn't matter. You could play with different algorithms, and you could take the risk, while for a big company, it's significantly harder. So I'll just kind of sum up and say that the space of possibilities is enormous. I mean, it's just absolutely huge. You could try so many different things, even if you don't change the algorithms around. I mean, each algorithm can be tuned to no end. And people have been trying for a very, very long time to do it locally. But the space is just so huge that you could try so many different things, and you could potentially have a huge, huge breakthrough in performance. And we very strongly believe that because of these changes in hardware and this solid state thing that sort of made people realize, wow, hardware changed so much in the past couple of years, or over the past couple of decades and the past couple of years with solid state. We could try all these different things. We could try all these algorithms. And a lot of things have started popping up in database research, like people have been trying log-structured merge trees, a lot of different concurrency algorithms that account for cache coherency, a lot of different things. And so we're finding huge, huge performance improvements, and we're hoping that a lot of other people are going to find huge performance improvements, kind of in different areas. And this database research and the idea of new databases, new innovations in the database industry will spring up because of these things we talked about today, and because of solid-state drives. So I'll just do a quick plug. We're hiring very aggressively, so if you know somebody, please shoot us an email, because it's very hard to find very good people. And thank you for coming in. I hope we're all going to enjoy our Sundays shortly. Thank you.
So we have a few minutes, about 10 minutes left. And if you guys have any questions about RethinkDB, about our philosophy, about anything that we've talked about today, we're happy to answer, although I appreciate if the lights can be turned up a bit, because I have difficulty.
Turned down.
Turned down, because I have difficulty seeing the audience. But if anyone has any questions, microphones. OK, great. So if anyone has any questions, you should come on up, and we'll be happy to answer.
How functional is it now?
So we're about halfway done. You can, but you're not going to get any of the performance improvements we've been talking about. So the system is functional itself, but there's a lot of, when you start playing with workloads, you get very interesting things. Like you get 2 orders of magnitude performance improvement on one workload, and then you get 2 orders of magnitude performance degradation in another workload. Like it gets very, very complicated as you start building the system. And you really have to account for so many different things that there is a lot of work involved. And I think we've been at it for about less than a year. And it will probably take another 8 months until we could start doing public betas and until we can give real functional software to people. That's a good question. I don't know yet.
Any other questions? About solid state in general, we also are happy to talk about that. We've amassed quite the body of knowledge over the past year or so. So if anyone has any questions on what the changes are going to be or how we see it shaping up, we're happy to answer as well.
Okay. I think there will be pretty significant changes in solid state over the next few years. And I can give you an example. So this example actually comes from graphics cards, and I mentioned them earlier, and from the gaming industry. And the idea was people build these really fast graphics cards, and you had to kind of talk to them through the CPU, but the moment you had to do branching or looping or all kinds of things like that, well, it was very slow because you had to wait for the graphics card to come back over the pipeline, and you had to stall everything. So what people did is they started changing the graphics card so that you could send a program down to the card, right? And with rotational drives, that never actually made sense because they're so slow, like it doesn't actually matter. But because solid state is so fast, you could send a program down to the solid state. So as you hop through your B tree, all you really do is, you grab a node, you kind of load it into your cache, you look up one thing, and then you send another I/O request. And then you look up another thing, and you keep doing it. And solid-state manufacturers very much recognize that it makes sense to send a program down to solid state, to do it on the drive, and just get you what you want, right? And that's going to be an innovation that's probably even more important than solid-state drives themselves. And it's going to cause probably pretty major changes in our software and the software of other database vendors as well. So what about, the question was, what about the interface between the solid-state disks and the operating system? Could you be a little more specific? I'm not sure what you...
Yeah, we hear you fine. Okay. Right here.
Okay. So my question is, right now these solid-state drives are emulating the interface of old devices. Okay. There's not necessarily any built-in reason except that operating systems and other hardware are already built to treat drives as drives. What about if the interface between operating systems and the devices changes to access the flash directly instead of treating it as a block device?
Sure. Well, I think...
Well, I mean, how solid state's going to be positioned is also going to change. I mean, if you just put it through something like SATA, I mean, it's not necessarily ideally suited to solid state. I mean, you're going to start seeing, I mean, we already see it in PCI Express, and it's going to be put, right onto the motherboard in future cases. I mean, there's no reason not to. And as people start to play around with Flash a lot more, you can use it in a lot of different places. And all these changes are going to be pretty drastic.
This is going to take a while to do it because it seems, I mean, the Intel guys, I don't know how much we could say about it, but basically, improving, giving more transistors is easy, but fundamentally changing interfaces is very hard for them. So I don't know. Do you have any information on how long it's going to take?
No, I mean, it's going to happen, but the point is that Flash is something that people can play with. We're not quite sure where it's going to end up. Right now, the simplest thing is to treat it as storage, but it can be used in a lot of different ways. So we'll see how it pans out. But the point is that between solid state itself, just the fundamental speed of it and how it changes the storage equation, how it throws the entire balance of power into disarray, but also how what Slava was talking about earlier about how solid state can be used in completely different ways. It can send, for example, potentially programs to the drive. All of these things are going to cause massive shifts in how we develop software and how the architecture is built. I don't know if that answers your question well, but.
Yeah, so when it's available, is it going to be a SQL database or a NoSQL database?
Good question. It's a good question.
Well, we're at the MySQL conference, so it's definitely a storage engine. I don't know if you have anything to add.
Well, the point is that the fundamental technology doesn't require, there's no reason for it to use SQL other than that, SQL is pretty popular. So, it could be done as a NoSQL database or as a key value store. And we're definitely playing around with some of that as well.
Quick question. Maybe you already talked about this. I'm back here in the corner here.
Okay.
Over here.
Oh, I see.
Maybe you covered this. I had to step out for part of your talk. when you get certain kinds of performance improvements, new applications become possible. Have you been thinking about, let's say you deliver what you hope to deliver, what it's going to enable? Is it just more of the same, or when does it become, phase change?
Yeah.
So we definitely thought about this a lot, and we have a lot of ideas about where databases are going to be, 20 years from now or 30 years from now, and what applications it's going to enable. But that's going to require a lot of other technology innovation. So I'll give you an example of what I'm talking about. I think fundamentally what people really want to do, this kind of the holy grail of databases, what people are really interested in. They don't really care about SQL, or they don't care about failover or clustering or any of this stuff. What they want is to get an IP address from somebody and start throwing queries at it. And if you have 1 transaction a day, that's great. If you have 1 million transactions a second, they just want to be able to have a database, have a system that supports whatever they need to do. If it's a computationally expensive query, they want to be able to run it as slowly or as quickly as they're willing to pay for it, willing to pay for the CPU power, right? So that's, when we were talking to customers, fundamentally that's what we found out. Now, in order for that to happen, a lot of other things sort of have to happen before. So for example, if you provide this as a service, you have to fix the latency problem, right? Because right now, Cisco architecture is about 30 years old, and it's fundamentally built in a way that causes high latency environments. So that has to be fixed. A lot of other things have to be fixed. A lot of ideas in the database world, how we run queries, that has to be fixed. So over a very long timeline, and 20 years in software is very long, I think this is going to be probably the one thing that's going to change. Now, that's not directly answering your question, because I'm not talking about applications here. I'm talking about where the database technology is going to go. But the great thing about these disruptive innovations is you don't really know where they come from, right? You can't predict what they are, because if you could, then it would be much easier to build them. So I guess the short answer is I don't know. The long answer is what I've given.
There is also something to be said for just looking at the database market as a whole. So for example, you have a one-size-fits-all solution that people developed, like, let's say 20 years ago, 30 years ago. As demands increase, but performance didn't necessarily increase with it, you see fragments. So you have people focusing on analytics, people focusing on OOTP, that kind of thing. And there is potential, if you have high enough performance at some point in the future, for you to, for example, if you have long-running queries and short-running queries running peacefully side by side, to be able to do analytics and transactions on the same database with the same software. But that's not a fundamental change, but it certainly is the database industry sort of shifting to adapt to the architecture of the day. So, I mean, I'm not saying that's going to happen, but the point is that it's going to reflect, how it fragments is going to always reflect the architecture of the day. And clearly the architecture is changing.
There's probably a lot of things people are going to try, whether whether it works out or not.
Right.
Okay. Parallel meaning what? Or you're talking about multiple machines, not just multiple cores. So that's definitely on the timeline. But the problem with what you're saying, so it's definitely a problem we're very, very interested in, but it kind of widens what we have to do so much that we don't have the resources to solve it. So at this point, we're focusing on squeezing, a huge, huge performance improvement out of a single box. And if we deliver that, we plan to move on to sort of horizontally scaling, but we're not working on that right now.
Yeah, our perception is that there's exists right now today already in people's production machines highly underutilized architectures, and if we can take advantage, we see with the same, we're not using any particular special type of solid state drives or any particularly special hardware. We try to just use what people are using in their machines today, and with that hardware you can get drastic changes. So it makes sense to start with that and then move on to parallel when it makes sense in the future.
Now, there are other people working on the problem you're talking about. There are definitely companies working on it, and we're really looking forward to seeing what they come up with. It's just a very hard problem. Okay? Thank you very much for coming.